really lucky to have Peter Mucha here today. Peter is in the Department of Mathematics over at UNC and has probably done more work on community detection on the underlying sort of methods for identifying communities of anyone I know for certain. He's worked both on the standard kinds of community detection models you're used to thinking about, and how is this cluster distinct from that cluster, but also invented a series of methods for understanding how community detections evolve over time. And so, Peter, the floor is yours.
Thank you very much. So I will try to give you a fire hose of information. Feel free to stop me when I am not making sense, not if I am not making sense, when I am not making sense. I can use this slide deck, which you'll have. You can find it in the same place that Jim's was. It's titled Duke S&H Workshop Communities.pdf if you want to follow along, because I know it's hard to see in the back. And it's sort of, as you get further into it, to the places that I will certainly not get to, but I'm going to use the 10 minutes I lost as my excuse. The reality is I wasn't going to get there anyway. Why I was doing this is not important, but I was once in a situation where I was doing a series of workshops with people for sort of like 7-minute strategic business pitch kind of things, and I showed up one night at the dinner for this, and they said, "Okay, Peter, you're ready to go tonight, right?" And I said, No, I'm not on the schedule tonight. And they said, "Oh, but you're a faculty member. You can do this. You can give a 7-minute talk without thinking." I said, No. I can give a 60 or a 75-minute talk with no preparation whatsoever, but to actually like fit it into 7 minutes, that takes real work. And so what you have here is just going to be a fire hose of information. I'm happy to have this conversation go, sort of wherever it does, and hopefully I still give you a few spots where there are some big picture themes that you can make use of. So what those themes are really going to be, that if you sort of take nothing else out of this next, I don't even know what time it is, this next hour, since I'm standing between you and lunch, which is also another great position to be in, is I want to try to talk to you a little bit about sort of what is this game of community detection in networks and why it might be useful. I want to give you a couple perspectives. It's an enormous field. I can't possibly do the whole thing, but I want to give you a few perspectives on how you calculate these communities, and a real stress that this is an exploratory tool. A lot of what you do in public health contexts in particular, for the large number of you who are there, is you have models and you fit models to data, and then you use those models fit to the data to justify conclusions. And community detection, to me, from an applied mathematics perspective, is really much more of I have data and I'm throwing tools at my data to try to make sense of my data. And then once you make sense of the data, then maybe you can do some other cool things with it. But we're going to only touch a little bit on the what can you do with the data in sort of the why are they useful thing. So a lot of what we're going to be talking about are descriptive statistics rather than generative statistical models. But I will at least give you a couple pointers to why you really can't even see that in how bright it is. So that's going to be a useless pointer. So we'll talk a little bit about stochastic block models. And then the piece of the talk that we're not going to get anywhere near, but you can see the slide deck, which is sort of where do I think community detection is going in the future, because data gets much more complex. It's temporal. It's multiplex. There's a lot of community detection research that's active ongoing today that is about how do you extend these tools to more complicated data. Here's your obligatory enormous apology that this is a hugely self-absorbed presentation, but maybe according to Jim's intro, that's okay for me to claim that I know something about this. It's an enormous field. I don't pretend to even know it all, let alone present it all to you. There are two really good references for sort of surveys and reviews. They're getting dated. Now, this is a very fast-moving field. And so a survey article that I wrote with Mason Porter that was published back in 2009, I call it a survey because you can see from the page numbers that it's under 20 pages. It's readable. You can sit down. It's kind of pleasant to read. It's got, not maybe beach reading, but you know, it's not bad. Whereas Santo Fortunato wrote a tome of a review at the same time. It's 100 pages in physics reports. If you've ever opened up physics reports, that's one of those like little tiny print ones that you're glad with modern devices that you can, you know, sort of pinch and zoom and actually get it to a size that you can read. The rumor on the street is that Santo is working on an update, which will be awesome because it maybe will include a lot of the things that are at the end of the talk. So this is what I hope to do with what we're doing today. And because it's very self-absorbed, I need to really stress this is not me. This is all these people who I really am grateful to work with, a whole bunch of different faculty. They're color-coded by that's sort of the closest thing to Carolina Blue that I could get to happen in PowerPoint. And I used to be faculty at Georgia Tech, so that's sort of some of the yellow where my relationships with those people go from. So a ton of faculty, collaborators, people who I worked with when they were postdocs, grad students. I have a ton of undergraduates in my group. I'm the undergrads at both Georgia Tech and at Chapel Hill are really wonderful. And so some of these names show up in some of the references throughout the talks. And one of them, I guess, one name I should single out is Mason Porter, who he and I go back more than a dozen years now, back to when he was a postdoc. But I think I cite him here more times than I cite myself, possibly. So he only shows up as initials occasionally and lots of funding. All right. So with all that intro, what is a community and why is it useful? So here's your sort of cartoon picture of a community, courtesy of Aaron Clauset. Along with the philosophical disclaimer. These are more or less real quotes from what I think was the opening meeting of the second year of the Duke Network Analysis Center. We all sat around the table over when we used to meet in the Social Psych building, and Jim thought it would be a good idea to introduce everybody to sort of say a few words. And so he's been accused of turning everything into a network. I've been accused of turning everything into a network and a graph partitioning problem. Basically, I don't just stop that it's a network. I want to take that network and I want to ask, how do I slice and dice it up into groups so that I have a nice, simplified notion of what's going on? And there are lots of reasons to do that some of which I hope to convince you of in this talk, but the general duality is that whatever the process is that's going on the graph, whether it's spreading of a disease or of an idea, or it's friendship formation, its opinions being changed, this notion of the function that's happening on the graph is very tied to its structure. And so it's useful to me that if I have a hairball here, and this hairball can be simplified into thinking about it in terms of three large groups, and maybe those three large groups going further over to the right can be thought of in terms of smaller subgroups, then this is an easier way to think about how information might flow on the graph, how diseases might spread on the graph, and is just generally useful, I think. Now, the big caveat, which is that this is sort of obligatory. So who has ever heard of Zachary's Karate Club? Okay, a few, but lots no. Okay, so I will surely botch the social science history of this, but I'll at least tell you the urban legend as it spreads around in the world. So Zachary might have been one of the luckiest people ever in terms of studying a group and having something awesome happen to that group. Jim talked a little bit about the Christakis and Fowler data, and how, it's this happenstance that buried in this historical data, they were able to tweeze something out that had a signal in it. This happened to Zachary in real time. So he was studying a karate club, like actual, like at a university, 34 individuals, they all get together on a regular basis, they train, they fight, all those good things. And then somewhere along the way, again, don't rain on my parade if this is not true. So then at some point they had a fight, not a cool Bruce Lee fight, but but they had a disagreement over the future of their club, and they fractured into two rival clubs. Now, my armchair psychologist perspective, what would I do? maybe that's what a mathematician would do, is not the normal way to think about how a social structure should work. So, but what I would do in this situation, if I really cared about whatever the disagreement was, then that would surely influence which group of people I would go to. But far more likely, for the vast majority of these 34 people, whatever the fight was, I don't know, Jim and Sally, they're having an issue. So which club are you going to go with if you don't have a real dog in this fight? You're going to go to the subclub where all your friends were. And so this is, in fact, what happened. Zachary mapped out every one of these nodes as a person in this original 34-person club, and the links between them were the observed friendship ties between individuals. And when they had their argument, they split into two rival clubs. And in fact, they split at the spot where really any notion of trying to take this data and splitting it into two groups had better find that these are the two groups, modulo maybe a couple of these people in the center, because you can just sort of see the right side of the picture has much denser connections within them than relative to the left side of the picture, and vice versa. And this partition of the data into sort of left and right, and in fact, you can see I sort of divided it by some other cuts here. So I, in fact, divided this up further into 4 groups. It optimizes a particular quantity called modularity that we'll talk about later, which is the direct measurement of this notion that I just said verbally. How many ties are there within the groups relative to what you would expect at random in some model? And we'll talk about what that model is a little later on. But just as what's the game here is we want to find groups of nodes in the data that are more tightly connected to each other than they are to the rest of the network in some sense. And there's many, many different ways to do this, and that's kind of be part of the main message of this talk, is that there's lots of different methods of community detection, and you're going to get to play with multiple different kinds of community detection later on this afternoon. And in fact, using the Karate Club is sort of a wonderful story. You get to stand up here, you get to like maybe kick, in the air if I were younger, and you get to have sort of fun with it. But as a test of community detection, it's really just a good story. And if your method doesn't work on this, if it doesn't find these two groups or nearly that, then go home. And this is a direct quote from Eric Kalakshik, who's a statistician at BU, who organized a whole program year on the study of complex networks out at the SAMC, which is the Statistical and Applied Mathematical Sciences Institute here in the Triangle. And he got so sick of seeing versions of this picture in the opening workshop that he sort of spouted this. My colleague Mason is kind of a cheeky, humorous, sarcastic fellow. So in about 5 minutes later, he had a whole web page on Cafe Press where you could buy that quote on a T-shirt with a picture of unfortunately, the last I checked, this is a lie. You can't actually find it on Cafe Press anymore. Mason assures me that in his copious free time, it will appear one day again. But if you really need a T-shirt that says, if your method doesn't work on this, go home, I can hook you up. So I can do that. This is such an overused example. And I think I'm telling you all this to say, like, don't get overly enamored with the Karate Club example, please. It is so overused that there's, in fact, a Karate Club club. There is a little trophy. I don't know that you can see it so well here. There's a little trophy that travels the world to network science conferences. And the first person at the conference who uses the Karate Club as a piece of their talk gets inducted into the club and gets handed the little trophy. And I'm still bitter that I missed this by like one talk. And one YY On at Indiana University, he used the Karate Club in what I thought was a truly gratuitous example in the talk before mine. And so I'm not in the club. But all right, so if you're not going to use that, let's talk about some other data where I think it's not just 34 nodes and you're looking at it and you sort of go, oh, well, I do a force-directed diagram and it's sort of obvious. I would just sort of snip it right there. Let's use community detection to explore some more complicated data. And so this is one of my favorite examples. Again, apologies that this entire talk is incredibly self-absorbed. This was some work led by Mandy Trod, who at the time was an undergrad at Carolina and then stayed on to do her master's degree before getting a PhD in biomath at NC State. And so what we were looking at here was a snapshot of the Caltech Facebook network from the fall of 2005. So 2005 is the dark ages, you know, on the time scale of Facebook. This was back when you needed a .edu address still to have a Facebook account. And so, so this is 762 individuals at Caltech, or affiliated with Caltech, that is, it actually had caltech.edu addresses. And it looks like a hairball, right? We've sort of connected them together by their declared Facebook friends as of that date in fall of 2005. I've tried to already lead where the discussion is going to go to sort of give you a preview of what's going to pop out of the community detection by putting down colored symbols for some of the nodes according to what house the students are affiliated with. So at Caltech, the students all arrive. They very quickly sort themselves into these residential houses. At the time of this, there were 7. Now I think there's 8. So you sort of look at this, and just even in this hairball of a force-directed layout, you see, well, there's a lot of green diamonds over here and a bunch of blue circles up here. And so, you know, granted, lies, damn lies, statistics, and visualizations. I happen to think that a really good visualization is a very powerful way to look at the data, but you got to do it with a little buyer beware of, you know, is that real? And so let's see if it is real in some way. What we're going to do is let's throw a community detection method at this, and we're going to still be optimizing modularity, and I promise we'll talk about what modularity is before we're done here. So when we do that, that same data groups into a bunch of communities, where what we've done here now is we've represented each of the communities as a pie chart. The size of the pie chart is proportional to the number of Facebook users who got placed into that community. And the color codes on the pies are in fact just, they should be the same color codes back on here. So if we look at this group here, for example, it's more than 3/4 of it is from the maroon group. And then a bunch of other ones are represented, and then there's this big purple chunk. I could go on, back to the professors can talk forever. I could tell you a whole 30-minute IRB nightmare story about this data and how we got it, and but every time I do it and I try to tell it as a, you should be. Every time I tell it as sort of a, you should beware about sharing everything about your identity on the internet, no one seems to care. So it's, we all go ahead and keep doing it anyway. But so the bigger issue here from a why is community detection useful here is that, well, just even as a visualization of the data, it seems to be, eyeballing it, that there is a very strong connection between this piece of demographic data, and we had other pieces of demographic data I'm not showing you. I'm just jumping to the one that's the good answer, right? That the house affiliation, that is where do these students live, seems to be very strongly connected to these identified groups. And again, the idea of the group is every one of these pie charts is a community by this notion of modularity, which means there are more connections, significantly more connections within the group than with the other groups. And that, basically the people that you live with, you're much more likely to be connected to than other people at the school. This one's very dominated by the maroon. This one's very dominated by the yellow. This one's sort of split between 2 houses, and back to the IRB nightmare. It's, in fact, those are 2 buildings that are right next door to each other on one side of campus. We weren't supposed to know that. It was easy to figure out. We weren't supposed to know which numerical code was men or women, but they gave us the data for Wellesley. So, it's it's not hard. Right. Question, please.
Tell me a little bit about how you generated this net. Was it just based on attributes? Because I'm trying to understand.
Right.
In my head, I'm kind of jumping to, it looks like what you're doing is imposing structure via attributes instead of letting the structure drive.
I'm glad you asked. Right, so because we're using the attributes here only for the visualization. The network underneath this is the Facebook friendship network. without any of the attributes information. So we're taking the adjacency matrix. So the workflow is we take the adjacency matrix that is the Facebook friendship, again, on this one particular day in September 2005. We're partitioning that network that has no information about the attributes, no direct information about the attributes, into communities. And then we're looking at how the communities relate to the attributes. So these groupings, these big circles, if you like, the boundaries of the pies, the grouping them into, here's a community, and here's another community, and there's some number of connections between those two communities. The big boundaries of the putting nodes into the buckets is only the adjacency matrix. The splitting it up into a bunch of little pies is now looking at all the nodes that are in that bucket and asking how many of them are labeled maroon, how many of them are labeled yellow, how many of them are labeled cyan, how many of them are labeled purple. Is that?
So are you using equivalents, or how are you partitioning that?
So we're partitioning by optimization of modularity, and I'll come tell you more about that. Yeah. So this is the convincing you want to pay attention when I bore you with the math later. So it seems by this procedure, it seems that we can identify. So we're really doing two things here at the same time. We're putting everybody in the buckets, and then we're taking a look at the demographics within the buckets and seeing that there seems to be a strong correlation between this attribute information and this structural information. And then again, it's sort of one that makes sense because you would think you're a college student, you're much more likely to be affiliated with the people in your own house. I neglected to tell you one thing that might further convince you of that. In this setting, the norm is virtually everyone joins a residential house their first week on campus, and they're in it for all 4 years. So, it's a very strong clustering phenomena into the houses. Now, there's one color, of course, to which this does not apply. Purple. Anybody want to take a crazy idea what purple is? All right, off campus is a good guess. Not in a house. Now, you got to remember, this is also, both of those answers are good guesses. This is Pasadena, California, where the cost of living is, everyone lives on campus, right? That would also be good. There are a few graduate students and faculty and staff peppered into this data. And if you try to look at more recent data, you have to do a much better job identifying who are the active students. These are all excellent ideas. These are all things that one should ask. In this case, no. All right. This is Caltech. That would be like 40% of the population. This is no. In fact, what this is where the scary Big Brother piece is supposed to be. They're the people who didn't say what house they're in on their Facebook page, right? And they didn't. Their house affiliation is just blank on their Facebook page. But if I were a betting person or I were running an alumni event, I was running some sort of social event for this maroon group, you can bet I am sending an invite to everyone in that purple wedge. I don't know for a fact whether or not this is true, but I'm willing to bet that this is a really simple missing data imputation by community assignment process. There's a lot more you can do with this data that I should probably not go into at length, but you can look at things like sort of the normal thing, and I guess you guys will talk about ergums and things like that later. You can do regressions on the original adjacency matrices and ask questions about how important it is that people are in the same class year, or how important is it that they live in the same house, or that they went to the same high school, with regards to is there a tie between two individuals. However, when we have communities like this, you can also ask questions about, well, how much does this structure correlate with a given attribute? And so we're going to do this by a particular thing called the z-score of a Rand coefficient that I hope to at least show you one or two slides about later. It's basically just, it's a particular pair counting statistic here and how many standard deviations outside of the mean in a random distribution you are for that pair counting statistic. You can measure, is there an influence on what major you are in here? Is there an influence on where you live? Is there an influence on graduation year? And so all these things are in fact influencing individual ties, and they are influencing the group structure, but some of them much more strongly than others. So this number here, 222 for House, is way bigger, 222 standard deviations away from the mean. That's highly significant for residents. Yeah, and I could go on and talk more about those numbers, but let's show you at least one other example or two other examples of why I think it's useful to slice and dice your network up into groups. And this one is one that I always sort of feel like we can get our hands around, particularly in a political season. So we're going to talk about roll call in the U.S. Congress, and we're going to talk about it as a network. And this is a very different kind of network than lots of other network data in the sense that it is dense and it is weighted. And so it's not like here's a picture of a particular scientific co-authorship network where every node is an individual and every link is that those two individuals have co-authored at least one paper together. In contrast, this is a blue to red heat map color coding of the 100 by 100 adjacency matrix for a particular 2-year period in the US Congress, where we've zeroed out everything on the diagonal, so that dark blue is 0. And what we're measuring here for every pair of senators is what fraction of the time that they were both present did they vote the same way, either up or down, but they voted the same way. And so the deepest, darkest reds are people who are in near perfect agreement with each other. The darkest blues away from the diagonal are disagreements, and obviously I've already manipulated the indexing of this adjacency matrix so that I kind of have a group up here that you can eyeball at the level of the matrix, and I have another group down here. Or if you're kind of parsing and you're looking at it like, well, you could ask, is there really sort of one group here and then a slightly different smaller group here? I mean, there's lots in this picture already that talks that speaks for me to the idea that there are multiple different ways to try to slice and dice this network up into groups. Either I can have a very coarse resolution into 2, or I can look for sort of 3 groups, and I could go deeper and deeper into this. And then you get little wonky things down at the bottom if you're really up close and you're paying attention. So I lied to you, this is in fact a 101 by 101 adjacency matrix, because somewhere in this 2-year period, one of the senators either died or retired or had a sex scandal or I don't know what, but he got replaced. So this is another way that I find useful to think about grouping nodes into communities. This is for the so-called 85th Senate. There weren't any political science people in the room, were there? Oh, there was one. Oh, good. So not to put you on the spot, like you memorize these numbers, but what time period is the 85th Senate? Okay, so you don't study. So right, there's 5 subfields of political science, and you're in one of the other ones. Okay, so the 85th Congress is 1957-58. And, there's nothing controversial going on in American politics. To be clear, if this is being recorded, I'm going to be equal opportunity and bash both sides of the aisle. So they must really hate me. But, yeah. 1957, 1958, there's nothing controversial going on. Just the first of the major pieces of civil rights legislation in the civil rights era of American politics. And so here's sort of a bigger version of it that you can see. You might ask, okay, well, if that's what it looked like during this very high stress period of American politics, what does it look like today? It kind of looks like this: my team versus your team. This is actually a few Congresses ago, so it's highly polarized. Jim and I had a paper together a few years back that's a nice visualization of this polarization in this roll call network. All credit for how cool the visualization is goes to Jim. So we looked at sort of historically back to the mid-70s out to, we keep saying we're going to update this data, and I owe you an updated data file, but up through 2012. And so what we're measuring here is we're measuring how polarized is the network, that is how, and here the notion of polarized is how easy is it to identify those two groups, right? Red team, blue team. And so sort of how far apart are they is on the vertical axis. And you can see that things are getting more polarized as we go towards the present. And we're also looking at sort of the simultaneous hollowing out of the middle of the Senate. So there's a lot of people that don't as cleanly fit into one of these natural groups, and they're occupying a middle space, but they've kind of all disappeared. And so it's depressing. One last example, and then we'll get on to what are some of these things, because this is where I get to sort of, I get to talk about why, all of these networks look like graph partitioning problems to me, because it's useful to think about all that data down to the level of these different groups. So here's a completely different network. This is, these are the strains isolated from 337 urinary tract infection patients who presented at a particular clinic in St. Louis, Missouri. And what we have done, so every dot is one of these clinical isolates. So it's the E. coli bacteria. Usually when I give talks like this about communities and networks, this is an actual true story. So now I guess I won't say usually, I'll do it right now. The origin of this study is that the friend of mine who had access to this data saw this awesome visualization and asked me, so, okay, imagine the senators are E. coli bacteria. and the way they vote is that they have different genetic virulence factors. So the E. coli genome is very complicated. You can sort of just pile extra stuff onto it, unlike ours. And so there's not a simple binary, you have gene A or gene B, but you can have both. And so that's effectively what's going on in this visualization here, is that every dot is an E. coli bacterial strain, and they're voting in the sense that they have this they have one of a handful of genetic virulence factor genes. That's redundant. They have one of these genes, and so what we're showing here is sort of grayscaling the links between them. It gets very dense up in here. The links between them are a measure of how correlated the gene presence in one is with the gene presence in another. Have you told them about bipartite networks and things like that? Okay, so this is a particular, both of these examples, right, the roll call and this, are examples where we've taken bipartite network data. In this case, it's clinical isolates and genes, and we've projected out one of the modes. So now we're just looking at a network of the clinical isolates. And the neat story here is, again, you can sort of eyeball it, but the color coding helps with the eyeballing. So we're showing a particular force-directed layout. We maximized modularity under a particular set of conditions, and we found that it splits reasonably robustly into 4 groups. You got this big red group, green group, blue group, and then you can argue about sort of these black outliers here. But the part here isn't just we split it into communities and now we pack up and go home because we're done. It's, well, what can you do with those communities? Do the communities tell you something different than if you look at the graph as a whole? So just like the attribute data for the Facebook network, and that the attributes are statistically different within different groups, here we looked at things like, well, what's the host sex, male, female, across the 4 groups? What's the resistance to the 2 major antibiotics that are prescribed across the 4 groups? And now this is just showing you the numbers of the 4 groups. And this is still very far from clinical significance, because what our big dream is, now that we've done this for genetic virulence factors, we also want to do this for metabolomic profile data. My collaborator's dream is new person presents in clinic, here's your cup, go off to the bathroom, come back. I can his dream is stick that in the mass spec, figure out which community the patient's infection is in, and that information now would influence a lot for you which antibiotic you prescribe. If you identify that the infection is in what I'm calling here community 2, well, that'd be a pretty bad idea to give them Cipro, because they've got a 75% chance of being resistant to it. Whereas if they're in group three, the big green group up here, oh yeah, you want to hand them that Cipro. I mean, they're very, very likely to be susceptible to it. The missing link in this is knowing whether or not this works from metabolomic data, and that's an area of active research that we're doing. Okay, so hopefully we've now convinced you. If you aren't convinced, I'm sorry. I got nothing else. No, I have hours worth of stories like this. So you want to pretend you're convinced, even if you're not, so that I move on to the next part of the talk. So if it's so great to have these groups, well, what good are they? If I've said that they do this and they're good, how do I actually find them? And this is the spot where I'm going to give you one very narrow view through modularity-based methods for calculating these. And I'm going to want to stress, and I'll fire hose you with slides later in the deck, to other methods. And one of the really great things that you'll do this afternoon in the lab is you'll use multiple different pieces of code inside of R to generate different communities. Because hopefully all these stories I just told you about these different examples doesn't depend on the method that I used to identify well-connected groups. Or if it does depend on it, I'd better have a pretty good reason why it depends on it, right? I don't want to reach conclusions that are only based on modularity maximization or a particular stochastic block model. But so with all that caveat, let's tell you a little bit about these. And and again, this is an enormous field. This is just examples of all the different words and titles of different things. Many others I'm sure I've missed. Go look at the survey or the tome of a review if you want. Let's just tell you a little bit about what the game is in modularity and see if we can make some sense of it. So we're back here to these pictures from Aaron, and we're going to slice and dice these up by modularity. And so I introduced this to you in words before as a count of the number of connections you have within groups minus what you would expect, or relative to what you would expect at random. And whenever somebody says to you the words "at random," that had better already come with the big asterisk, in what model, right? So they better tell you something about this. Just writing this out notationally here, picking a particular notation, what we're going to do is we're going to talk about a matrix B. This matrix B is not your adjacency matrix. The adjacency matrix, the data you have is Aij. It could be weighted, it could be directed, it could even be multi-layer and temporal and all sorts of things, but right now it's just a matrix, Aij, talking about the connections between nodes I and j. And whatever the at-random model is going to be is P. So really B is just formally the difference of these two things. So it's the expected weight of this edge relative to random in whatever model you picked, and I haven't told you what model yet. I'm just denoting that model by P. And so what modularity is going to do is it defines a quality function to be optimized. So Q is my quality function. We're going to optimize it so the prefactor doesn't matter. We're just looking for the biggest value of Q. And what we're doing is we're summing over the elements of this matrix, again, just a difference between data and random model. But you're only going to include the elements of this matrix when I and j have both been placed in the same group. So if Ci is the assignment of node I to a community, and Cj is the labeled assignment of node j to a community, delta is just an indicator function. It's 0 or 1. It's 1 if they're the same. It's 0 if it's different. And so we include this factor if and only if Ci and Cj are the same. And now we've set it up as an optimization problem. So this quality function, this modularity definition, is a function of the labels that you assigned to the nodes in the graph that you have. And now you pick the labels as an optimization problem so that you get the biggest possible value of Q that you can find. There's lots of there's lots of, then studies about how this works. There's all sorts of issues about the computational complexity of it, which are both a feature and a bug in a way that I'll show you in a graphic in a little while. There's lots of packages. You're going to get to play with lots of things in the iGraph library in R this afternoon. But a key thing to be thinking about here is what's the null model? And a lot of this will be under the hood. You won't worry about it when you're just using vanilla packages for modularity in R, which is fine. It's if you start thinking about how you might extend these to other kinds of data sets, that then you really, really need to think hard about what this appropriate null model is. But it is useful in saying that to know one thing about the standard null model. And so the standard null model is a so-called Neumann Curve null model for Mark Neumann and Michel Gervin, and here's all your references for it. And the null model here is that, so how do you define Pij? Pij is the expected weight of the edge between I and j. So this is actually, I should back up and say, this is the null model for an undirected network. It can be weighted, but it's undirected. And so you're assuming that you have independent edges distributed through your data, subject to the constraint that the degree sequence stays the same. Or if it's a weighted network, that the strength sequence, the weighted degrees of the nodes stays the same. So this is a more complicated random graph model than the Erdős-Rényi model, where you just assume that all the edges are there IID with probability P. Here, the probability of that edge, so if these are in fact, if it's an unweighted network, then expected weight is the same thing as probability, right? I bounce back and forth between the words because we throw lots of weighted data, and you can use this same null model for the weighted data. This is how we handled that weighted data for the roll call network, for the genetic virulence factor network between the E. coli, what have you. If it really is just an unweighted data set, then Pij is the probability of there being an edge between I and j. And basically, the independence assumptions really quick. This is like a back-of-the-envelope calculation, because the independence assumptions require that it have a product form like this, so that it's some function of ki, the degree, or if it's weighted, the strength of node I, times the same function of the degree of node j. And now if you start playing games, so if this is a requirement of the particular independence assumptions up to the constraints, and then you ask yourself, well, now how do I pick the probabilities so that I actually get out the weighted degrees that I am constrained to expect? Then if you sum Pij, say, over j, then you're summing over all these functions of some j, that's some constant. You don't know what that constant is. But so you have some constant multiplied by some function of the degree of I. I should have brought a blackboard or something, or I should have written this out. But basically, on the one side, you have the degree of node I. On the other side, you have some unknown constant times a function of the degree of node I. The only way that this works for all I is if the function is just proportional to degree, because you need to have a little ki sitting by itself on both sides. So now you know that this function's just proportional to ki, this function's just proportional to kj, so the whole thing is proportional to the product of ki and kj, and then you work out what the constants are so that you actually get out the expectations that it literally is back of the envelope. It's not just something that you sort of say. Now that said, I've also kind of lied to you because I stuck a gamma in here ahead of time. And the gamma is also useful to know about because it's a so-called resolution parameter. The gamma has sort of a funny little history. It's literally the physicist's ad hoc, and I say this sort of, again, equal opportunity offensive to different fields. I have a physics degree, so I'm throwing myself under the bus when I throw the physicists under there too, back in my past. The gamma is just an ad hoc extra numerical factor that got stuck in at one point for the purposes of being able to tune a dial and either get large groups or very small groups. If gamma is very small, I'm going to break one of my rules of presentation and go back. if there's a gamma inside this Pij and you tune it down so it's really small, then most of the B data just looks like your adjacency matrix minus some small things. And in fact, you can tune gamma all the way down to 0. And this becomes now the world's dumbest optimization problem, well, or easiest optimization problem. Because if there's no P here, then the math says what I'm doing is I'm assigning labels to nodes so that I maximize the number of edges that I have within the communities. Well, how do I maximize the edges within the communities if all I'm doing is and it's not relative to anything? The way to maximize the number of edges you have in the communities, you take your whole connected component and you say it's a community, right? Because now all the edges are in the community. So you need this term here to put a little pressure on you to not have just one big group. And as you make the term bigger, as you make this P piece that you're subtracting off larger and larger and larger, at some point you cross over to a threshold where nothing in the B matrix is positive. So there's no reason to group anybody with anybody else, and now you just have the world's maybe second dumbest optimization problem, which is that, if there's no gain from putting two nodes together, then I'll just give them each of them their own label. And so gamma is just like a little knob. Chris Danforth at Vermont, to sort of paraphrase him at this point, he likes to say that every microscope needs at least one knob, and this is the knob, and there are options to use this knob inside the iGraph package.
Could you play with that then to see how community-ish your network is?
You can, yeah, and I will try to show you one picture of that in a little while. But yeah, that's in fact a piece of the story, is that you can use that. Although sort of that now it's really an art at that point. I mean, it's like my old AM. None of you are, it's like I'm old enough that my first car had an AM radio, right? No FM. I mean, it was like, and I mean, I had to tune that analog dial, and it's kind of like you found the signal. And this resolution parameter can kind of act like that. You're like trying to find the signal where it let the data tell you that there's a community there. Oh, look at that. It's the next slide. Okay. So it wasn't the next slide until I clicked through. So great. I planted you, I guess. So here's an example. This is some data that's from some financial exchange data, but that's in fact what we're doing. So there's a lot going on here. The only one I want you to pay attention to is the Magenta Curve. So what we're plotting is the number of communities that we found as an easy measure of did things change versus this resolution parameter. The default value is 1. If you sort of don't set a resolution parameter at all, that's the default. And this particular data, I mean, all the little black lines are spots where we took little discrete steps in gamma, and how big were the differences in the partitions that we found, that is the community assignments that we found at those different gammas. So there's lots of differences, lots of differences, lots of differences, and the number of communities is sort of also changing by little amounts. But when you get up to this region here from roughly just above 1.4 to almost 1.6, there's a nice big flat plateau, nice big strong signal coming through on your AM radio, right? That there are no changes between any of the partitions that we found in that range, and so they all have the same number of communities. So that's an example right there. The picture on the right is from a paper where we, like the roll call data, only we were looking at resolutions in the United Nations General Assembly, and for reasons, there are 2 different resolution parameters here, so we're plotting the number of communities on the vertical axis versus these 2 resolution parameters, and sort of finding these big flat plateaus where we're trying to see if that's where the signal is. So I want to tell you one more thing about this null model here, is sort of my goal here is to make you intelligent users of this exploratory tool. And I think it's useful to, in order to really understand what you're doing and how community detection is in some ways different than just normal clustering of data, is because of the way, for instance, in this modularity measure, because of the way that you're respecting certain pieces of the underlying structure. In this case, you're respecting the underlying degree sequence of the data. And I'm sure this has come up in some of the other things that you've talked about, right? One of the features of a lot of network data is it's very heavy-tailed in its degree, or the degree distribution can be very Erdos-Renyi random graph-like. And so you want to respect that piece. If you don't think it's important to respect that piece, then sure, go ahead. Define your Pij to just be that every edge is there with probability P, IID. You can do that. I'll show you why that's often a bad idea in the next slide. But I do also want to note that the argument I made you before is the so-called Neumann Curve. You should know that if you have data that's directed, there's a different null model. It's Elizabeth Leicht and Mark Newman, where it looks very similar, but the product between the degrees of I and the degrees of J are in degree and out degree. And then if you can even do this directly on bipartite data if you want. If you do it on bipartite data, then the expected weight of the edge between nodes I and J is either some product of the degrees here. So the notation is that Ki is the weighted degree of the ith node in the blue set, if it's blue and red connected to each other in a bipartite data, and the dj is the degree of node j in the red set. And so if you grab a node from blue and another node from red, then there's some non-zero expected probability of an edge between them, or expected weight of an edge between them. But if they're from the same set, and it's bipartite data, there are no connections from blue to blue or red to red. So question first, and then we'll work around. Yeah.
And do you feel like that's problematic when you're doing community protection, given what we know about the importance of conditional dependencies? And I guess my other question is there a way that you could take like the results from ERTM and then put that into your algorithm and then go from there? Or is that just kind of crazy?
I don't know, that's crazy. It might be computationally too burdensome for anything large. I think what you're saying is exactly spot on about understanding the assumptions underneath this. And I think one of the key take-home messages that I'll say in response to that is, again, this is an exploratory tool. Modularity, at least, is a descriptive statistic that you're using to explore the data. It's not a generative model. So yes, you are measuring the excess, if you like, or you're measuring the number of edges relative to this very simple underlying independent up to some basic constraints model. And you're optimizing labels that maximize that quality function. But you're not fitting a model to it that assumes that independence. And so in fact, your question is exactly what I want to say about what worries me often about stochastic block models a few slides from now. If I instead am fitting a model to the data, but I'm not respecting these things that we know are true about networks, that bothers me. As a descriptive statistic, that bothers me a lot less. We can maybe talk more about that if you want.
So my question was about whether there's a distinct advantage to using a bipartite model here rather than a Neumann curve, and if you could just do a one-mode projection aside from like retaining the salience of the second mode. Like I'm thinking of the Southern Ladies data set.
Yeah.
It really matters that you went to the event at the Governor's Mansion as opposed to Stella's Tea Party, right? And
Right.
You would care about that.
Right. In which case you do want a group for that.
Right.
And the best example I know for this from my own work is in that United Nations data set. We identify lots of resolutions that have to do with issues of Israel and Palestine as the salient resolutions that keep popping up in a group that seem to be related. So there is sometimes real value in staying with the original data and not projecting out that information.
But it would be more theory-based rather than like if you have bipartite data, you should definitely use the Barber as opposed to the...
Well, the one lie I'm telling you here on this slide by incompleteness is that In general, you're going to find it harder to find software that will run this efficiently for you than this. Is the sort of maybe honest user's point of view. And so there are a lot more tools in your toolbox after you project it down. So why wouldn't you just, but maybe I guess the question I was going to ask is why wouldn't you just use the Erdős-Rényi model? And maybe this does also address your questions about, it is important to understand the sensitivity of the model to it. So this is a wonderful data set of political blogs back from the 2004, in the period around the 2004 elections, color-coded sort of obviously red and blue. The nodes are individual blogs with a, sort of a political leaning leading to the coloring of them in after they've been grouped. The sizes of the nodes have to do with the in and out links of these blogs. It has a very sort of core periphery structure. There's a densely connected core in here. There's a bunch of, at least at the level of the data set, there's a bunch of other outliers here that don't play a whole lot. And if you try to use the Erdős-Rényi IID probability P random graph model here as your underlying relative to what model, then you tend to group instead the core relative to the periphery. Because what you do is by taking everybody who's in the core who has very large degree, much higher than the average in the network, if you take all of those nodes and you call them a group, then you get a very high count in your quality function. The fact that the things around the outside aren't giving you a lot of contribution to your quality function, well, that doesn't matter because you sort of maximized your count here on the inside if all you're doing is comparing to what the average degree is. It's only by respecting the degree sequence and asking about what are the connections of a given node, given that it has the expected degree that it has, that you get clean breaks into team blue, team red. I should say, as just an aside, since I put this other picture on down here, that there's lots of other methods that aren't hard partitioning of the nodes into groups. Everything I've talked to you about today assumes that I'm going to assign a label to a node. Not 3 labels to a node, not leave a bunch of other nodes that I don't know how to classify, right? Both of these issues of having overlapping community assignments and also the possibility of sort of having background unclassified nodes are important possibilities that sometimes you need to take account of. And here in this data set, what is happening is, in fact, there's sort of a blue core and there's a red core. And then there's a bunch of other things whose activity is so limited that it's not really clear that they're on one side or the other. This hard partitioning problem that everything else I've talked to you about today is forcing me to choose these green nodes and either call, every one of these green nodes I have to decide, am I going to call it blue or am I going to call it red? And that might not be all that salient to the underlying dynamics, whereas something that's deep in this core here, is blue, and something that's deep in that core over there is red. So I say this is just something to know about. I'll skip the next slide. And I'll just also maybe say one more thing here. Now this sort of transitions us into implementation questions. So far, I've told you and I've given you long lists of names of different methods, and then I've only talked in depth about modularity. A big takeaway I want you to remember from this conversation, if you can, is that in a lot of this community detection literature, there's really 2 questions that are related to each other, and I'll re-emphasize this again later. But one of them is sort of the underlying method. Well, method's a bad word here. The underlying, in principle, theoretical method that you're using to try to define communities. So this idea that there's modularity. There's this function that you can measure on any partition of the nodes, and I'm going to go try to find the partition that maximizes that, right? That's sort of, in principle, what I'm trying to do. And then there's in practice, what does an actual code do when you ask it to go try to do this optimization problem? What computational heuristic does it use? How the heck, for those of you who, if any of you worry about computational complexity, who saw the words NP-complete go by, and thought, but I want to do this on large networks, and that's bad, right? How is this actually going to work on real data and when I implement it? And so lots of the different things that you're going to be using today are different computational heuristics, all of which are trying to maximize modularity. And the fact that there are multiple different computational heuristics are in part because, well, there's on different size data sets. You know, if your data set is really, really large, you want to use sort of the fastest and most efficient thing that you can possibly find, even though it might not find a great optimum for you. If your data is much smaller, you can do something much more complete and computationally expensive. It turns out that modularity has this terrible bug that is also a wonderful feature. So I sold it to you as an optimization problem. I want to try to find the labels, so the set, singular, of labels that maximizes this quality function of modularity. And these visualizations are from some great work from Aaron Clausette and some collaborators of his. So this is a stylized curvilinear coordinates plot projected down into just a 3D visualization of modularity versus sort of where are you in this complicated label space. Every one of these points on this crazy landscape is a set of labels onto the network. And so for some sets of labels, you're sort of down here at low values of modularity. But if you get yourself up here near the peak where I told you want to be, and you zoom in on this peak, the peak looks like this. So every one of these points, again, is a different set of labels. Some of them, because we've projected it all down in just a 2D coordinate space, some of them are very close to each other. Some of them, you know, that are roughly near each other have very significant differences. This is a stylized, reducing yourself down to 2D visualization of that complicated space of partitions. You can see there are a whole bunch of little local maxima trying to find the set, singular, that is at the absolute peak of this thing is probably crazy. And again, it's an NP-complete hard problem. By that, what I mean is it's equivalent to you actually would have to test every single possible assignment of labels to nodes in order to know whether or not the little tiny local hump you're on is higher or lower than some other local hump somewhere else. And so on one level, this is terrible. And you're then thinking, why did I waste the last hour of my life listening to this guy talk? You might be thinking that for other reasons, but you know, if the whole idea is that's terrible. But in fact, I'm going to tell you this is really more of a feature, right? Again, there might not be a single set of labels that are a good representation of your data at whatever scale of resolution you want to have. Think about that 85th Senate data again, right? There is a two-community split of the Senate into Republicans and Democrats, and because it's 1957, 1958, there is a three-community split of that same data into almost all the Republicans, all of the Southern Democrats, and all of the other Democrats. Right? And with a handful of the Republicans getting tossed in with the Southern Democrats, right? So and the difference between that two-community split and that three-community split, which one has the highest level of modularity? Actually, in the political science literature that studies roll call, a very common thing they do is they throw out so-called nearly unanimous votes. And now you say, well, what's nearly unanimous? I know what unanimous is, right? I mean, unanimous is, you know, this is actually a funny real bill. Unanimous is everyone voting unanimously to congratulate Sammy Sosa on his 500th home run. Yes, that was a real bill in Congress. And in retrospect, not such a good idea, but how that kind of played out in the long run. But nearly unanimous, they pick a threshold. Some people say 97%, some people say 97.5%, and they just throw out everything above it as just meaningless noise because, yeah, you're just congratulating Sammy. Depending on where you set that threshold, the two-community split or the three-community split wins. Same adjacency matrix, except for you're throwing out just a handful of bills over here. Now, does that matter? Like, does it really, in a situation like that, does it really matter which one has a modularity of, I'm making up the numbers here, so don't quote me on them, bless you, 0.402 versus 0.401 or 0.403? No, they're both different representations of the data. I would argue to you that everything up here on this landscape, this very glassy, complicated landscape of partitions, they're all individually meaningful representations that simplify what your data looks like. So this is not a bug, this is a feature. And this is in fact why the heuristics work. Because depending on the details of which heuristic you're going to use, and again, you're going to use some different heuristics, the heuristics are very good at getting up the hill. And so you can get to this space that's up near the top of the hill very, very fast. And then the differences between the heuristics have a lot to do with, well, what kinds of features do you tend to gravitate to when you're up there? So having multiple different computational heuristics to solve the same theoretical optimization problem is a benefit, because it's going to give you access to many different possible partitions to test for whatever your hypothesis is in your data.
But with your drug example,
Right.
if this is a choice for a whole population
Right.
about whether or not they're going to get a drug, and you get that wrong,
Right.
then maybe that's not just a question of whether this Congress had this many petitions or that many.
Right.
It's whether or not this many thousand more people will die if you get it wrong.
Right, and so in that, I'm glad you asked that, because in that example, right, that was only one representative labeling of many of the partitions that we studied. They all have the same robust features of the red core is mostly a community, the green core is a community, the blue core is a community. And then there's a whole piece of the literature that's about so-called consensus communities. How do you take multiple different sets that have been identified as potentially good communities and now try to, squeeze those all down to give you one consensus kind of labeling? And these are the kinds of things that you do have to be aware of as a user. Like, don't just run it once and take your labels and go home. Like, if you're gonna try to do something serious with those, then you want to make sure that your result is robust. And if it doesn't work for some methods versus others, you want to know why. You want to at least be able to come up with a reason why. So I'll tell you about just one of the methods here, so that you can sort of think about the computational heuristics about this. So again, in the space of what is the in principle theoretical problem optimization of modularity that you're trying to solve, and what is your computational heuristic? This is a particular heuristic. It's called the Louvain method. It's by Vincent Blondel and a bunch of his collaborators. There's great code for this now I should have put the link. I meant to put the link. It's probably findcommunities.google pages or something like that. Literally, if you Google find communities as one word, I'm sure it will pop up. It's a beautiful paper. It has two really great ideas in it, which my postdoc mentor would have said is two more than most of the literature has. But the two ideas are right here on this same slide. So what they did is just some really wonderful algebra of the modularity quality function, and they came up with a bookkeeping procedure that showed them which quantities that they had to hang on to in order to efficiently calculate how much modularity changes if you take a single node in or out of a group. And so if you can do one of these, right, now you can do anything, right? Because you can move from any set of labels to any other set of labels by, sort of one at a time moving a node in and out of the group and putting them into the group that you want. And so they sort of identified, so this is all the guts that are in the code that you as a user don't need to necessarily worry about, sort of which different structures, which quantities did they have to hang on to in memory so that they didn't have to completely painfully recalculate the whole quality function for every partition if they were only going to move one node at a time. The second idea is also really great, which is that if they started with a network, so this is a very small little toy network here, and so there are no labels on it initially, and now they're going to do modularity optimization, moving one node at a time in and out of groups. And in this particular example, they happen to have come up with 4 groups, so blue, green, red, and whatever this cyan or gray, I don't know what that is. So they've identified it into 4 groups. If you take this set of labels onto communities. And so this was the best that they could find by just moving one node at a time. Which again, if you think back to that political example of the Civil Rights era Congress, right, you can't get all the Southern Democrats merged with the Northern Democrats and kick the Republicans out over into the Republicans easily one move at a time without having to explore a whole bunch of things that are going to be low modularity. So now how do you move multiple things at a time? And their heuristic is they reproject all of this for community labeling down onto just a graph of 4 nodes. And that, in fact, if they do this in sort of the most basic way you would imagine, counting up now the weighted edges between this, the notion of how to calculate modularity using the Neumann Curve Null Model on this graph is the same as it is up on this graph. And if you move these nodes around, you can calculate modularity on this little tiny graph, and it's equivalent at all stages to what it was as if you had taken whole groups. And so now they're taking these 4 groups and they're merging them together. And in this particular example, they merged 2 of them together. So the blue, well, maybe it's the other way. The gray and the red merge together, and the green and the blue merge together. And so now they've basically just got 2 groups, and that's their best modularity, and so that's where it spits out and gives you the answer. So it's very fast. It runs on very large networks, and it's wonderful. So I just wanted to mention that one to you. And what you're going to do in the lab, as I understand it, is you're going to play with a lot of really great things that are in the iGraph package in R. I do want to point out to you that there are other things to be aware of that I don't believe you sort of have as easy of access to in R. But again, if you want to become something more of a power user of these things, of these tools, that they're good to know about. So I'll give you some links here to mapequation.org and to the graph tool, which runs in Python, and of course the Louvain code in its fine communities format runs faster than I believe it does inside of iGraph in R, though there is, right there, cluster Louvain is one of the methods that you can use inside of iGraph. And so you're going to get to play with some of these different things. The rest of the slide deck really just sort of tries to make sure you know that there are other things out there, right? So one of them is this map equation that I gave you the link to on the previous slide. It's a different method. It's about random walks on the graph and about how to now group things based on what the description lengths are for your random walker. Here it's a citation network, so they're bouncing around through the literature. And if you're sort of going from citation to citation or things cited by and cited tos, then you can sort of random walk yourself around, and depending on how you choose to label those graphs, and you now talk about, well, your random walker spent, was in economics and economics and economics and economics, and then after a certain number of steps jumped to healthcare. What is the information theoretic amount of data that was taken to give this description? And so they've got some great code. Martin Roswell keeps a really wonderful website with some great code that runs these things. Santo Fortunato has a method called Aslam, and some of his collaborators. So since he wrote that sort of tome of a review, this one's really useful to know about. I also give you some links to ideas of conductance. Conductance is an old idea of networks and graphs. So now it's really a cutting problem, not how to maximize the number of edges within the groups, but how to minimize the number of edges that you have to cut in order to separate the network into groups. So it's also a very powerful optimization problem. And there's some really, really great work by Yuri Leskovic and Michael Mahoney and their collaborators. And there's a whole host of different papers, so I didn't even try to cite them all. But if you look up either of their works, you can find lots of things. They like to plot lots of what they call network community profile plots. So here what they're doing is they're plotting for you conductance. So it's a minimizing problem. You want to make conductance small, right? You want to cut very few edges. So how much do you have to pay to cut your network into groups versus the size? Because again, every good microscope needs a knob, right? Versus the sizes of the groups. And so these little dips are good cuts of the network. So this is a spot where cutting it into that many groups, I'm sorry, cutting them into a set, misspoke, cutting them into a group of that size gives you one cut of this network. Going a little bit further down, there's a cut that separates that wonderful Karate Club plot, because again, if your method doesn't work on this, go home. And lastly, I'll just say some things about stochastic block models, since I'm now literally standing between you and lunch. This is a whole different approach. Right? This is a generative model approach. And there are tools for this. The mixer routines inside of R are a good way to go at this. Tiago Peixoto's work on the so-called graph tool in Python is just brilliant and runs on very, very large networks. The idea here is that you have a block model of your graph. So here's a very simple block model. This is what I'm trying to denote here by the heat map are the color, are the probabilities of there being an edge between a node. So I've got 4 blocks, and so if you sort of think about this 4x4 matrix, this element is a high probability of there being an edge from group 1 to another node in group 1. And this is the probability of an edge from a node that's in group 2 to another node that's in group 2. In this particular example, we happen to have made all these other probabilities very small. So if you think of this as a model for generating a network, then a representative example that you'll get out of this model is a very dense core group here, slightly less dense group here, and then even slightly less denser groups here, with then some weak number of connections between them. So the blue here isn't 0, but it's smaller than the densities within the groups. You can have lots of different kinds of block models. Here's just a few stylized examples. Here's a 3-block model with representing 3 tightly knit communities, 3 communities, each of which is tightly knit within itself. So you have high probability within group 1, high probability within group 2, high probability within group 3, but you can have many other kinds of probabilities. These words core periphery have been tossed around. Core periphery is just a different kind of block model. So this is a little 2x2 block model probability matrix with a high, you now labeled all your nodes 1 and 2. 1 is the core. So there's a high probability of links from group 1 to group 1. And there's a very low probability of links from group 2 to group 2. These are the things out in the periphery that are not as connected to each other at all, but they all have to be well connected back into the core. Right? You have to actually get to them. And then you can dress these things up as much as you like, and you can make a lot more pretty pictures. And again, you'll have some fun this afternoon. I think, there's, maybe this is sort of the last big take-home that I'll just say, which is, then I lied. I won't get to the how do you compare communities, but you can see lots of references in the slide deck about those. While you're running these things, try to be aware of what are the underlying assumptions of the model, what are the underlying optimization problems that you're trying to solve. What might that mean? Ask these critical questions. What might that mean given the data set that I have? Because lots of times that will drive you to think about, well, is modularity with Neumann Curve the right thing to do? Well, it's certainly not the right thing to do if the data you have isn't of the kind of things that get assumed that are on it. If you have a directed network, don't use that null model. If you have bipartite data, you can't just feed that adjacency matrix into your model. You have to either use the bipartite null model, you have to use a code that allows you access to that, or you have to project it down into a setting where that is appropriate. If you want to use stochastic block models, be aware of the assumptions that are in those. And then be aware that there might be many different computational heuristics for solving the same problem. You're going to play with lots of different ones for modularity today. But for stochastic block models, I've sort of given a teaser to the graph tool, and I mentioned Mixer and R. Which implementation you use for trying to fit your stochastic block model to your data will drastically affect your runtime, will drastically affect the quality of your results. So you need to be aware that there's this duality of sort of the theoretical problem that you're trying to solve and the implementation of it. There's a lot more in this slide deck that you can see about comparing partitions, about the, as I told you at the beginning, we weren't going to get to it, about what's going on now. And I think I'll just sort of close by reiterating that this is exploratory, right? That nothing about, I mean, you can start to say, well, stochastic block models are a generative model that I'm fitting to my data and that I'm now going to think of as a way of thinking about my data. I would argue, based on, I'm not just using your question for stochastic block models instead of for modularity, even stochastic block models are very simplistic models that you would never use as a generative model of a real data set that is supposed to be clustered, and it might have high transitivity, for example, or it might have clustering based on different attributes. That's why you're going to learn about exponential random graph models. And so being aware of these things is very useful. But using them as an exploratory tool can help you to ask a lot of other questions about your data. And I think that that's where a lot of the power is. This is coming up multiple times through your questions today, and so I'm really, really glad that it came up. There are many methods for doing community detection. If you're going to put lives on the line, you better make sure that your result is a result about the data and not a result about a particular implementation of modularity on that data, right? So be aware of this. Don't tie yourself down to one method. Check for robustness of these things. And then the end of the slide deck, the third part that I knew I wouldn't get to, has a lot of things about, well, what do you do with so-called multi-layer networks? These are representations of things that might have multiple different kinds of connections and or change in time. It's a really powerful way to look at lots of data. And the methods for doing community detection are really still just coming online for how you handle these things. So there's lots of teasers to different pieces of the literature in that piece of the slide deck. And if any of you ever need any more information about any of this, I'm more than happy to try to help.